All right, we're back for lesson 4 on the quantum mechanical model of the atom. So I was trying to say in our last video that the atomic orbital is this area of space, there's your previous video, is an area of space where the electron is supposed to be found. And because the electron has wave-like properties, its wavelength for a given energy sort of limits it to a certain size. The electron can't be located within that size. The electron becomes that space. So that space is that's that three-dimensional space around the nucleus. We do know that the electron at least wants to be around the nucleus because electrons are negative, nucleus is positive, so the electron does want to be near the nucleus. But because the electron is wave-like, as soon as it gets close to the nucleus, we can't really know where it is. We can know its energy, and from its energy we can guess that for that amount of energy the electron must be in this approximate space, and it'll be some sort of shape. Okay, so these are quantized. These use quantized values to best describe this energy, or to best describe the shape that could have a certain energy. So we're going to use 4 quantum numbers to describe this function. Think of it as any old function like like y equals f of x. Y equals f of x. Here we have a function that's the value of x. Here we're thinking about an energy. That's the energies that Bohr is seeing in his spectra, and it's essentially equal to the function of NL, ML, and MS. So energy, or the orbital, is equal to the function of NL, ML, and MS. And this is some craziness. This is the actual function. And just like in our generic functions we use in pre-calculus, y equals f of x, where f is some function, right? It might be mx plus b, right, which gives us a linear line. It could also be like ax squared plus bx plus c, like a quadratic. Or it could be something crazy, which is what the case with the wavelength one, or with the wave function. But it's a generic function that when you give it these 4 values, you get an energy. And if you do this thing and then you take the square of it, you'll get if you take the square of it, you'll get an orbital shape. So this gives us the shape, this orbital. Anyways, I don't want to get into that. Okay, anyways, so electron orbitals are described in terms of these variables. There is the first variable. These are what you need to know. I'm going to try to really cut it down from what I said in class, just because I know I talked a lot about this and maybe to the point where it got confusing. There is the first value, n. N is principal quantum number. It's the most important one. It's how far from the nucleus. That's all you need to know. N equals how far electron is from nucleus. Okay, and that's like super important. It's more important than anything. N is how far the electron is from the nucleus. If you have to choose between 2 different electrons, one has an n equals 3 and one has an n equals 4, and you had to choose which electron is more reactive, it's always, always, always going to be the one in the n equals 4. It'll be the one that's higher. The higher the energy, the more reactive. Higher the n, more chemically active. Okay. Secondary value, the secondary quantum number, L, is the angular momentum. So this is a weird one. This is the idea that for a certain amount of energy, there can be multiple solutions that give the same energy. One way to think about that is that the electrons have a minimum quantum, or they have a minimum sort of wavelength. So if the distance, let's just say this is r, is, if the distance is some value, then if the distance is small, then there can be only one wavelength. One wavelength that fits. When r is farther, there might end up being more than one solution. So there might be the original solution like this, but there might also be, or there might be the original solution, which is to have one shape. This might be an allowed solution, but now that it's a little bit bigger, it's bigger than the minimum distance, the electron might be able to flip in on itself. And so what I'm trying to get the connection here is that something like that. So like this is sort of this is half the wavelength of the previous, but it has the same energy. I don't know if that really works. Another way to think about this is, let's think about this. Let's think about it more like, no, I think, I'm on the right track. So this, let's just say where this R up here, oops, no, use the eraser, to this R here, let's just say this is the minimum R for an electron. And then, so as the distance to the nucleus gets longer, we can either get a sort of inversion there, or we can choose a new shape, or we can choose the original type of wavelength, which has no nodes in it, or we can choose to invert at that node using that sort of minimum distance again. I'm not sure how perfect or true this model is. And then every time you get farther away from the nucleus, you create more opportunities to make different shapes, like so. Or, I probably should have done the second one first. And so some of these shapes share characteristics. This one here and this one here both have one single inversion point. If you do this in 3 dimensions, you get these very cool shapes. And these shapes turned out have been labeled with letters. So the S shape, which turns out to be a very sharp line on your spectrum, is this sphere. This is the shape if you have no nodes, no points of inversion. A single point of inversion creates what is known as a p orbital. 2 points of inversion gives you a d orbital. 2 inversion points, f orbital, and 4 inversions. So this is our 1 node, 2 nodes, 3 nodes, 4. Okay, so the idea here is that you need a certain amount of distance from the nucleus before this is possible. So that's why the equation is up here. We have, for L, L can have any value up to n minus 1. So if n equals, if n equals 1, then the only value you can have is 0. But if n equals 2, you can have 1 or 0. If n equals 3, you can have 2, 1, or 0. And if n equals 4, you could have 2 or 3, 2, 4, 2, 1, and 0. And these shapes get really weird and complicated, but they are that sort of shape. So here is the no node shape. It's a sphere. So all 3 of them are spheres here. These are just different n values. So this is n equals 1, n equals 2, n equals 3. And so we've called them 1s, 2s, and 3s. S here is for the spherical shape. And then the first number is for the n, for how big they are. Notice they get bigger each time. Over here we have the L equals 1 orbitals. Please note the error in the book that I wrote ML and it should be L there in the book. So we get the p orbitals. So we have the 2p, the 2px, 2py, 2pz, and you can see them all. In this case, these are all the same type of orbitals, same size, but because this has a direction to it, we end up having to create 3 different ones. We'll talk about that in a second. Important, the wave nature of the electron means it is the shape of the orbital. It is not flying around in a figure 8. It is everywhere inside the shape at all times. This is the minimum size and minimum area that an electron can take up if it has this amount of energy. That's probably the best way to think about it. I often in my head take this little shape and I think about, what if I took this and I spun it around into a third dimension? Then wouldn't it sort of start to spin around, 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 and you would create sort of 2 sections like that. And that would be where this dumbbell shape comes from. It comes from spinning spinning the sine wave around a third dimension. These ones get way more complicated. This is where these are your d orbitals. There's a whole bunch of interesting shapes here, but you've got essentially, this is the one that I always use to remind myself that it's 2 nodes. But 2 nodes can be done in a lot of different ways. If you want to look at, say, this one, you can see that there is a node that is kind of going along the x-axis here. And then there's another node that goes along the y-axis. And that's where my 2 nodes are on those 2 planes. F orbital, we have 3 divisions, or 3 folded shapes, 3 sort of cuts, and they're really wild. But again, you can kind of see a shape here that looks like that, and then just imagine spinning it this way, and this is the kind of shape you'd get. So when you read these L values, this is the shapes you want to read. Now, if you are comparing an n, so if your n is equal to, this means that if n equals 2, then L can be either 0 or 1. This is n minus 1. N equals 2 implies a distance. A distance from the nucleus. So I'm going to start with my electron, and my nucleus. I'm going to put a shape here like that. Here is my L equals 0 shape. Within this L equals 0 shape is my other L equals 1 shapes. So I'm going to take my purple marker here. So within this same shape is L equals 1. Remember that n implies distance to the nucleus. So L equals 1. Oops, I hope I'm not covering the microphone. So L equals 1 has to be within the same radius, controlled by, this is the radius here, right? This radius, which is proportional to n. So radius increases with n, or it's dependent on n. So radius depends on n. And so if you set n equals 2, then the radius has been set. So now all of these orbitals have to fit within this radius. And this can be confusing to students because they can often think that these electrons are not touching. But instead, we have to think about, no, these are all electrons with the same amount of energy, or slightly different amounts of energy, and they are going to be occupying the same space. And these are the different ways they could occupy the same space. Okay, I think I'm happy with that. So you can fill out this little chart here. If the principal quantum number is 1, then you can only have one subshell. So notice that you always have the same number of subshells as your number n. Those subshells will always have a value up to n minus 1. So for n equals 1, we have only the L equals 0 subshell, so we only have s orbitals. If n equals 2, you'll have s and p orbitals. For n equals 3, s, p, and d orbitals. And it goes on forever. We are never ever going to look at g orbitals. You can look them up online if you want. There's pictures of them. But they don't have any meaning because on our periodic table, we have no elements that have g electrons in their ground state. All right, so we saw that some of the shapes have direction. Actually, all of the shapes have direction except for s equals 0. So because they have direction, we have to have a number that tells the difference between these directions. So this is called the magnetic quantum number, and it is about the orientation in space. What direction is the orbital facing? This is an interesting quantum number because usually, for example, in the px, py, pz, they don't change in energy. All three of those have essentially the same amount of energy, so their ML value is kind of inconsequential. If it has ML equals 1 or ML equals 2, ML equals 1 or ML equals minus 1, it doesn't really matter in terms of the energy of the shape. So up here we could go back to this one, and we can think about this shape here, this px. We can think about this as ml equals 1. Py would be ml equals 0. And pz would be ml equals minus 1. All three of them, L is equal to 1, L is equal to 1, L is equal to 1. All three of them, N is equal to 2, N is equal to 2, N is equal to 2. Pauli exclusion principle states that no two electrons can have the same quantum numbers. So this is a one way that the electrons can differentiate themselves and occupy the same space. So electrons cannot occupy the same space if they have the same quantum numbers. They must have different quantum numbers. This is what stops us from falling through tables and falling through the floor. All the electrons in our feet and on our hands cannot, as they get closer and closer together to the other electrons and we push on them, the quantum numbers become more similar because the space the electrons are occupying and the energy the electrons have becomes more similar. But because Pauli exclusion says that two electrons can never have the exact same quantum numbers, we can never push our way into an object, because our quantum numbers and the quantum numbers of the electrons that we're trying to push on, those ones will never be the same. Okay, so that's our ML value we're doing. The ML value can have any value up to L plus and down to negative L. So if L is 1, so for subshell, for example, for S equals 0, then ML can only equal 0. If we're in a p orbital, then we're talking about ML is equal to 1 or minus 1, 0, and 1. If we're talking about a d orbital, then ML would be anything from minus 2 to minus 1 to 0 to 1 to 2. And this is where the 5 orbitals come from. And you can continue that to F. That seems like a lot. The last thing that they noticed was that any electron any orbital seem to also be able to fit 2 electrons into it, and that's because there are 2 possible solutions for this 3-dimensional space. You could start with, thinking about back to my model of imagining a little wave that goes like this, and then we're going to spin this wave in 3 dimensions to get our shape. If you're going to spin it in 3 dimensions, it doesn't matter if you started your wave this way or this way, right? As soon as you spun them in 3 dimensions, you would get the same shape. So here's our same shape. I'm trying to make it a 3-dimensional shape. So we get the same shape no matter what. It doesn't matter if the wave was going one way or going the other way. And if you really, are desperate for an answer, here we have the wave function, but this is the wave function squared. And when you square something, you hide some of its features, especially features like negatives. Remember that if you took -2 squared, that would be 4. And if you took +2 squared, that would be 4. So we can think about this as, or in this case, we're going to talk about 1/2. Here, this could be +1/2, and this is -1/2. Otherwise, all the other values are the same. And so when they are squared, they get the same result. But Pauli exclusion only says that the quantum numbers have to be different. It doesn't say anything about the shapes have to be different. So that's what happens here. We have a new number, ms. It's the orientation of the spin axis of the electron. You don't need to know what that is, but it is the reason this happens. You are starting with 2 different sets of quantum numbers. So these are both our different sets of quantum numbers for our wavelengths, for our wave function. And then these wave functions squared end up looking the same. They're the same. They have the same they occupy the same space. All right, that's the most complicated thing you'll ever do in this class, I hope. So, but, this is the real summary that I want you to attract your attention to. Size is determined by n. So it determines which electrons will react most of the time. L is the shape number. It's important to determining what type of bonds you can do. Also will be a tiebreaker when choosing reacting electrons. So if you had n equals 3 and L equals 1 and L equals 0 electrons, it would be the L equals 1 electrons we'd expect to react first out of those 2. The ML values, they allow for the P, D, F, and F subshells to hold many, many more electrons, or many versions of those electrons, but those ML values, we aren't even going to really play with those, honestly, other than knowing how many there are. You really just need to know how many orbitals per type. That's the real key thing that I want you to keep in your mind. And then the plus or minus, this is, it actually allows for 2 electrons per orbital, or you can think of it as limiting 2 electrons per orbital. There's no other options. Okay, hopefully that helps us a little bit, and I'm going to let you play around with that. Maybe we went through these in class already, so I'll just leave this up for a quick second. If you need to copy that down, you can just pause the video here. Otherwise, we'll talk about electron configurations probably in our next